Hey guys, welcome back. In our last tutorial on Lamport's logical clock, we saw how they perfectly capture the causal order in the distributed systems. But there's a catch. They can't reliably detect the concurrent events. Two unrelated events might get different timestamp or falsely suggesting one happened before the other. That's a real issue for systems needing to handle conflicts like replicated databases. So today we are going to upgrade to vector clocks, the smartest solution that not only preserves the causality but also precisely identifies when the events are truly concurrent. We have three servers, A, B and C. We will maintain a vector of counters over each of the servers. In this case, there are three servers. So we will have a vector of three counters that is initialized to 0, 0, 0. Similarly on server B and on server C. All of them initialized to 0. Now an event happens on server A. So we will increment the index of server A by 1. So this will become like 1, 0, 0. After that, we have to send the event to server B. In that case, first we will increment the counter of server A by 1 because this is another event. So we will increment by 1, that is 2, 0, 0, and then send it to server B. Now server B is the receiving end. We need to compare all the vectors of both the servers. So in this case, we have got 2, 0, 0, and on server B, the counter is set to 0, 0, 0. We will take the maximum counter of each of the received values and add 1 to the server's value itself. So here in this case, we will do max of 2, 0, 0, then 0, 0, 0 plus ti plus 1. This will become 2, 0, 0. This is the max, and we will add 1 to the index 1. So it will become 2, 1, 0. So now the vector at server B is at 2, 1, 0. At server C, an event happens at timestamp 1. So we will label it as 0, 0, 1. Server C sends a message to server B. So now if we send it to server B, we will do max of 2, 1, 0, and 0, 0, 1. This will incur to 2, 1, 1, plus we will add 1 to the server's index itself. So this will be addition of 1. This will become the new counter at server B will become 2, 2, 1. Do you see how we maintain the causality of server A, B and C? So when an event is received, each server knows what all event has happened in past. You get that, right? So this is how we do the vectors algorithm. Let's reiterate the algorithm. 3 simple rules to follow. First is the local event on processor Pi. We increment the value by 1 on the index of that server in the vector. When we send a message from server Pi, first we increment the vector of that server and then attach the message and send to the server. Upon receiving the message, we update the components by taking max of each of the vectors from the receiving server and the current server. And after taking the max, we increment the vector by 1 of the corresponding server. So this is how the algorithm works. Let's discuss some of the properties of the vector clocks. So vector clock provide a partial order on the events that exactly matches the happens before relationship. So this is very important, the happens before relationship. So for instance, if A happens before B, it is denoted by A arrow B. This indicates A happens before B. Let's compare some of the result. For instance, event A happens before event B if and only if event A is less than equal to event B and event A is not equal to event B. Strictly, there is an inequality between at least one component. And the same happens for the vice versa if we do event B happens before A. Now, event A and event B can either be concurrent or incomparable. If neither A happens before B or B happens before A, if these two conditions hold, then they either happen concurrently or they happen incomparably. That is, there exists some I where VAI is greater than VBI and some J where VAJ is lesser than VBJ. These are the important properties. Let's go a bit deeper over these properties. So for the vectors timestamp T and T prime. So T is equal to T prime if and only if for all I Ti is equal to T prime I. That is, all the values are equal in both the timestamp, both the vectors. Ti is lesser than equal to T prime. This means all the event in Ti is lesser than equal to T prime. T is lesser than T prime if and only if all the events in T are strictly lesser than all the events in T prime. Then T is concurrent or incomparable with T prime if and only if T is not lesser than T prime and T prime is not lesser than T. So based upon the timestamp properties provided above, we have come up with three properties. First is, for A to be occurring before B, the vector A should be lesser than vector B. For A to be happening concurrently or incomparably, either vector A should be equal to vector B or vector A should be parallel to vector B. This way, we will identify that the events are similar or happening concurrently. So this was vector clocks. There are still some of the trade-offs for vector clock, such as vector clocks are powerful but cost more because we have to carry all the messages of all the servers. So as the storage grows, it grows with the power of n. So in large system, there are some optimization they have done. So they are bounded vectors being used so that we don't have to store the complete range of servers, because there are so many distributed servers and we might end up storing a large array of counter. That way they have bounded vectors. So they are used in Amazon DynamoDB, Riak or Redis for detecting conflicts in eventual consistency. So guys, if this helped, smash the like button, subscribe for more distributed dives and turn on your notification. Comment below if you want a coding implementation or a real world case study next. Thanks for watching. See you soon. Bye.